Hi everyone, welcome to another teaching video by physacademy.com. In this video, we'll learn about electric flux and Gauss's law. We will start this video by reviewing Coulomb's law and the electric field of a point charge. Then, we'll learn more about how to use this law to find the electric field around charged objects beyond a simple point charge. Next, we'll learn about flux in the context of Chicago rivers. After this, we'll learn about the mathematical representation of an electric field flux. Then, in the context of algebra-based physics, I'll explain Gauss's law. Toward the end of this video, to compare Coulomb's and Gauss's law, we'll find the electric field of a point charge using Gauss's law to compare it with Coulomb's law. This part shows how both methods lead to the same results as we were expecting. Let's start with the history of these two methods. In 1785, Charles-Augustin de Coulomb in France came up with Coulomb's law. But a few years earlier, in 1773, Joseph-Louis Lagrange, a respected genius behind many mathematical methods in physics, had a different approach to tackling the same problem. But at the time, Lagrange's ideas went over the head of most scientists of that era. Plus, he was so busy working on all sorts of mathematical problems that it took almost 2 centuries for the science community to review and understand his work. Eventually, in 1835, Johann Carl Friedrich Gauss, in Germany, finished Lagrange's work on this topic and proposed a new method to find the electric field of charged objects. Gauss's method, in particular, is much more efficient when charged objects have symmetry in their shape. Alright, before going over Gauss's method, let's review Coulomb's law quickly. Coulomb's law gives us the electric force that 2 point charges apply to each other. Let's say our goal is to find the force that charge Q applies on QP. In this case, charge Q is observable, and QP is the observer. Based on Coulomb's law, the electric force that Q applies to QP is given using this equation. Here, Ke is Coulomb's constant, and it is equal to 8.988 times 10 to the power of 9, and its unit is newtons times squared meters per coulomb squared. But under the hood, Coulomb's constant comes from an invert of 4 pi times epsilon naught. In the context of algebra-based physics, we won't need to dive deeper into what is epsilon naught. For now, let's call it vacuum permittivity, which equals 8.854 times 10 to the power of negative 12 Faraday per meter. Permittivity is a diagnostic physical property that characterizes the degree of electrical polarization material experiences under the influence of an external electric field. For example, the permittivity of humid air is less than the permittivity of dry air. So, it is inversely proportional to the polarization of the medium. Like in biology we do our best to eliminate the effect of the observer on experiments, in physics, this is the same. Here, to make this equation an observable independent, we divide it by the charge of the observer, and we call it the electric field of a point charge at point P. Using an electric field instead, we know the electric field of a positive point charge, regardless of the observer charge, is always outward. The same is true for a negative point charge, the electric fields are pointed toward the charge regardless of the observer charge. Now the question is, how do we find an object's electric field rather than a point charge? Well, we kind of can still use Coulomb's law to find the electric field any charged object at a given point. If we assume these objects are out of breaks and each break is a point charge, then we could calculate the summation of all of the electric fields of each of these point charges. As you see, this method for a large number of charges or objects with complex geometry can become very complicated. This method is very common for computer software in the 21st century, and it is called the finite element method, but in the 18th century, without modern computers, it was almost impossible to use this method for complex objects. You probably already practiced a set of simplified versions of this method in your homework sets, like the following examples. The left example is a simplified charged rod. And the example of the right-hand side is a narrow disk. This issue became the motivation for Gauss to finish Lagrange's method. To understand Gauss's method, first, we need to go over the concept of flux really quick. The best example for learning flux is in the context of the flow of a river. A river's discharge is in cubic meters of water per second. But to measure the speed of this river, it is important to know the width and depth of the river. In other words, the effective area of the river. Because if the river is very wide and deep, then, for example, 100 meter cubes per second don't mean it is a fast and wild river, but if it is a very narrow and shallow river with the same discharge, then it means it is a very fast river. Also, the angle at that we set this area up with respect to the direction of the current is important. If this area is parallel with the current, then no water goes through it, and the flux of the water that goes through it is zero. But if we select an area that is totally perpendicular to the current, then we have the maximum and the best effective area to measure the current. The same analogy applies to an electric flux. Imagine there is an electric field in an environment, and the area where we are supposed to find the flux through it. There are three possible scenarios. Scenario 1, when the area is parallel with the field, we have zero flux. Scenario 2, when the area is perpendicular to the field, we have the maximum flux. Scenario 3, when there is an angle between the area and the field, then we have some random flux. To formulate this, we have the following equation. Here phi is the letter for flux. A is the area. E is the magnitude of the electric field. And we have a cosine of the angle between the normal surface vector and the field. Remember, in science, when we need to measure the angle between a surface and another vector, we find the surface's normal vector, then we take this vector as the reference vector of the surface rather than the face of the surface itself. Now let's see how Gauss's law uses an electric flux to measure an electric field. First, we must define a closed 3D surface. Here, we assume this closed 3D surface is a sphere. Then we measure the flux in and out of this closed surface. Like scenario 1, if flux in is less than flux out, there is a positive charge inside this enclosed 3D surface because a positive charge radiates electric fields, therefore adding some electric field to outward flux. In the second scenario, the flux in is more than the flux out, which means a negative charge is enclosed in this 3D area. Because a negative charge collects electric fields and reduces what is going out of this 3D surface. And if the flux in and out are the same, then no charge is enclosed in this 3D surface. Now let's compare the result of Gauss's law with Coulomb's law to double-check them. If Gauss's law is correct, then the final equation for the electric field of a point charge needs to be the same as Coulomb's law. We go back to our original setup for a point charge. The observable with a charge of positive q is right at the origin of the coordinate system. The observable in green is a distance d away from the observable. We know that the electric field vectors point outward if there is a positive charge at the origin. In the first step of Gauss's law, we need to define a closed 3D surface. For this, a sphere is an ideal geometry as the normal vector are pointed outward and parallel to electric field vectors, therefore, the cosine of theta is 1. This case looks like the first scenario. Phi in is 0. Phi out is the flux due to the electric field of the point charge at the origin. Let's write down Gauss's law. Phi in, or the inward flux, is 0. The enclosed charge in this closed 3D spherical surface is just simply the observable charge or q. Using the flux equation, we get the following expression. The normal surface vector is parallel with the electric field, so the cosine of theta is 1. The surface area of a sphere is 4 pi times its radius square. Here the sphere's radius is the same as the distance between the charge and the observer. After rearranging the equation, we get an expression that exactly looks the same as Coulomb's law for a point charge. Of course, this is just a simple case to compare Gauss's law for a point charge with Coulomb's law, and from a practical point of view, when we have a more complex distribution of charges, Gauss's law is much easier to work with for an on-paper calculation when a computer is not available. Thank you very much for watching this video. Please check our website, physacademy.com, or our YouTube channel for more practice problems. If you found it helpful, please consider subscribing to our YouTube channel to support our work.